So, hello everyone. Thank you for joining me today. I'm gonna talk about a recent post that I published on the Wolfram community. So you can go there and download the notebook that I'm gonna present today. So recently, Stephen Wolfram wrote a blog post on what is ChatGPT doing and why does it work, where he explains how ChatGPT and neural networks operate, and he discusses the limitations of GPT models when not assisted by external computational tools. So here we will use a different approach. We will walk through the technical details of training our own GPT model, even if it's going to be a small model, using the Wolfram language. So let's get started. So first of all, what is a GPT? We hear a lot nowadays, ChatGPT. Even yesterday was announced the GPT-4. But many people don't know what these three letters mean. So GPT stands for Generative Pre-trained Transformer, which is a type of deep neural network architecture based on a transformer that was introduced in 2017 by Google in a paper called All You Need Is Attention. And basically, GPT is a machine learning model that generates text based on the prompts it is given. I mean, like, for example, the GPT-4 that was announced yesterday. It's a multimodal model that also can combine text. It can input text as well as images. But basically, the architecture is going to be fairly the same. I see a first kind of request if we can get this Shakespearean GPT model to use some temporal metaphors. Maybe at the end we have some spare time and we can play. As a disclaimer, this is more as a it's going to be a pedagogical tutorial for training a small GPT model. So we don't expect to have this GPT model to write an entire Shakespeare play from scratch. Although we will see some ways to use some more powerful GPT models like GPT-3 or GPT-4. So to give you a quick summary on how GPTs work, the generative part means that they can generate text, a sequence of tokens, to be specific, while the pre-trained part means that they have been trained on tons of data from text, from books, from internet and other sources. And finally, the transformer part refers to this type of neural network used in a GPT, which specifically gives a decoder-only transformer neural network, which we will see in more details in the following parts. Some examples of large language models are the GPT models from OpenAI. As I mentioned yesterday, GPT-4 was announced, which is multimodal. ChatGPT as well, Codex, which runs behind the scenes in the GitHub Copilot. There is Google's Lambda and many more different large language models. So these models are special because they are very large, billions of parameters and range of gigabytes of text or images in the case of the GPT-4. So here we won't be able to train one of such large language models, but in our computer, on our personal computer, we can train a small version of it, having the same architecture. And for having some fun, we are going to try to train it using all the plays from Shakespeare. So the first part is going to be to convert the input text from Shakespeare's plays into a sequence of tokens. So when working with text data, we often use a process called tokenization. That's to break down the text into smaller pieces or tokens. And once we have these tokens, we need a way to represent them numerically. in our machine learning models. To do this, we use a vocabulary that maps each token to a unique integer. And for this tokenization, there are like different methods. Some more advanced techniques are the byte per encoding or the word piece. You can check them if you're interested. But their underlying principle is going to be the same as the one that we are going to use, which is the one word tokenization. So we will assign to each word a different token, and also add the punctuation marks plus the spaces in our vocabulary. So for getting all the Shakespeare plays, I've already created a list of all the lines from Shakespeare plays and I put it into a Wolfram Cloud object. And so you can directly download it. It's only 8 megabytes, around 8 megabytes. And here there are like some random sentences from these plays. And I guess that some of you have read some of the plays, and it feels quite familiar. So then here, these are strings. We can select only the lines that we're interested in, which are the lines that the characters from the plays are talking to each other. And for this, we can use the select and string stars queue to do also get only the lines where they're like characters talking. And also then we can use the string take to remove these quotation marks. And once we have these cleanup lines, we can split them into one-word tokens using string split with a word boundary. And another thing that we can do is to add this so-called end-of-sentence token, which will provide context later on and indicate the model when to stop a sequence and avoiding generating repetitive sequences. So that's why we are appending this end token at the end of each line. So we end up having around 100,000 play lines from Shakespeare. And these are like some 5 random sequences of such lines already tokenized. As we can see, there are like some punctuation characters as well as the spaces. Now we can, with this list of tokens, we can create the vocabulary, which is going to be all the distinct words or punctuation characters that appear in the text. For this, we can simply use union, and we get around 30,000 of such tokens, which is comparable to the current common English words used, for example, in the built-in function word list, which is a bit more than 39,000. As a comparison, we can also check what's the vocabulary size of one of the GPT models from OpenAI, for example, GPT-2, which was released in 2019, I think. There is like around like 50,000 sub-word tokens. They use sub-word tokens in order to reduce the size of the vocabulary, as well as being able to also to process non-English words and other strange characters from internet. So in the Wolfram neural net repository, we have already the GPT model available, so you can directly get it on the cloud or on a desktop notebook by using net model, and we can extract all the tokens there by getting all the labels from the output, for example, and we can see that there are like a bit more than 50,000 tokens. So we can also display some of these words from Shakespeare's plays, and we can see that nowadays these words are much less common, some of them at least. So the next part I'm going to explain is what is the tokens encoder and decoder. So in the Wolfram language, we have the so-called net encoder, that is going to determine an integer value for each token of the vocabulary. For example, the token love is assigned an integer value of 14,382. And if we want, for example, to create a vector with that represents all the tokens from the vocabulary, and we assigned a probability of 0 to all of them except to the token of love to 1. With the unit vector, we will with the netted decoder we will get back the token. This type of kind of sampling, it's called greedy decoding. Since we are always taking the highest probability to make the final prediction. In later on, we will see other sampling methods in order to get a better sequence, generated sequences of tokens, or better generated text. So at this point, I'm gonna first go on a higher level to describe what is a decoder-only transformer. That's like the model architecture that GPT's models use, and it's the following. So we have the input sequences. In our case, it's going to be text, a sequence of tokens. There is first an initial token or text positional embedding, which then is going to fit in this blue kind of block here, which is an attention block. And the attention block consists in a multi-head causal or masked self-attention. Then there are like a residual connection here, a layer normalization, which we will go into more details later on. That sometimes nowadays also found before the multi-head causal self-attention. A feed-forward layer, another residual connection, another layer normalization that, as I mentioned, sometimes it's found before it. And then this attention block is repeated. There's a stack of them, several of them. In our case, we're going to use 4 of them stacked together, but in large language models, they can be kind of dozens of them, much larger. And then there's this output embedding layer, and finally there is this linear layer that will project embeddings into a size of the vocab, and then finally the softmax will give us the probability distribution for the probability of the next token to be generated. So let's go into more detail in each of these parts of the network. So we will start with the initial tokens and positional embedding layers. So an embedding is a way of representing a token as a vector of numbers. So each token is assigned to a unique vector, which is learned by the transformer during the training. These embeddings capture the semantic and syntactic relationships between tokens and text. The dimension of this vector will determine the depth of the network, which in a small model will be 128. But it can be much larger. Like, for example, one of the latest larger GPT-3 models from OpenAI, the DaVinci model, is 12,288, this dimension. And I guess that for GPT-4, it's even larger. That allow them to accommodate even longer sequences of text and process them. So then there's the positional embedding. That's in addition to the tokens embedding, transformers have this. They need to include information, this positional embedding, in order to encode the position information of each token in a sentence. This is important because in the order of words in a sentence carries meaning in natural languages, as we know. And in our case, the positional embedding will be learned during training, but we could also use the sinusoidal positional embedding. Maybe in the future, in the original transformer model, in a future blog post, I will explain how to build your own sinusoidal positional embedding. But here, for simplicity, we'll use only the learnable embedding, positional embedding. And at the end, as it was found in the original paper, the results are practically the same. So now we can combine both embeddings, and we obtained this net graph using the function layer. So we can see here, this is the tokens embedding from a sequence of n tokens. It will generate this kind of array of vectors for each token of 128 elements. And the other one is the positional embedding, that at the end they are added together. All right. So we can represent this initial embedding with array plot. And for example, the famous sentence of Shakespeare, to be or not to be. And here, each row, it's representing one of the tokens in the sentence, and it contains 128 elements of each. And this is before training it. That means that after training, this will look a bit different. So now we go into the masked multi-head self-attention block layer. So that's this yellow part here in the diagram. And this is we will break it down into different pieces. So first, we're gonna see what is the self-attention mechanism. So the self-attention mechanism involves generating three different matrices called query, key, and value. And each of them contain a query, key, and value vectors for each of the tokens in the sequence. In this case, I'm just using this I am a student example sequence. And then we, to obtain these vectors, we multiply the initial sequence embedding by different learned weight matrices for the so-called query weight matrices, key and value. Once the query, which they are also learned during training. Once the query, key, and value vectors have been generated, the self-attention mechanism computes a weight for each token in the sequence by taking the dot product between the query vector of that token and the key vector for each other token in the sequence. So that's basically the representation of the dot product of the query and the key vectors for each of the sequence. And then there is also a scaling factor here which is the square root of the dimensionality of the vector. This is to stabilize it, to stabilize the training. So the product can grow sometimes. So it's in order to keep the numbers smaller. They figure out that this will stabilize the training. And then there is a softmax function to the scalar dot product to obtain a set of weights that sum to 1. And these weights are then used to compute the weighted sum of the value vectors here. And which represent the importance of each token in the sequence. And we will obtain this attention value matrix. So another final component, not the final, but One important component for GPT models is the so-called masked attention. So the masked attention is used to prevent the model from looking at future positions in the input. Basically, what we are doing is to, inside these softmax, we're adding a triangular mask of this sort, where there's like minus infinities. So basically, if the sentence is like all models are wrong, this would be like this dot product here. And then we are adding this mask. It will, after the softmax, all these values are going to be 0. So the model basically cannot predict the next token by looking at the future tokens from during training. That's why sometimes it is called causal self-attention as well. And finally, the part of the attention block that refers to the multi-head self-attention is these attention heads. The concept of the attention heads it's a way of parallelizing self-attention mechanisms to allow the model to attend to different parts of the input sequence in a more fine-grained way. So basically, they separate in different instances of a self-attention mechanism that operates in parallel with other attention heads in the model. Each attention head has its own set of query keys and value weight matrices, and this will allow to focus on different aspects of the input sequence. For example, by using multiple attention heads, the transformer model can learn to attend to different parts of the input sequence at the same time, which can improve the quality of the model and focus. One head might focus on the syntax, and another one might focus on the semantics of the sentence. After the attention head has been computed, its own set of weights, they are concatenated together. This would be like the schematics of this multi-head self-attention. They are concatenated together and then passed into a linear layer that will generate the final self-attention mechanism representation with the same initial dimension that we had. So typically, the embedding size is set up to be divisible by the number of heads. In our case, the embedding size is 128, and the number of heads that we will use is 4. So the dimension of the key vector will be 32. And yeah, there is a question from Bob. Does attention matrix scale like of the order of n squared? Yes, that's because that's why we have the dot product. That's true. So another component of the attention block is the dropout layer. The dropout layer works by randomly setting a fraction of the activations in the previous layer to 0 during each training iteration. It has the effect of reducing the capacity of the model and preventing it from relying too heavily on any one feature or set of features. So that prevents also the overfitting during training. We have a built-in dropout layer in the Wolfram language, as we will see. And also another important part is the normalization layer, which I think that this type of normalization layer was introduced in 2015 for in-deep learning models for image recognition. And since then, it has been ubiquitous in any deep learning model. So the normalization layer is used to normalize the output of the previous layer, which helps to prevent the activations from becoming too large or too small. So this normalization is done by centering and scaling the activations to have zero mean and unit variance, respectively. So a final other important component is these so-called residual connections, which involve adding the input to a layer to the output of the layer before passing it through the next layer of the network. This has the effect of creating a shortcut or a skip connection that allows the gradient to bypass to the layer and flow directly to the next layer. So this role of residual connection is to address the problem of so-called vanishing gradients, which can occur in deep neural networks when the gradient signal becomes too small and to effectively update the parameters of the model. So the model will stop learning. So they are an important component. So now we can put all these previous layers that in order to create the masked causal self-attention block using the built-in functions of attention layer, dropout layer, normalization layer. And this is the function for this self-attention block using function layer. And we can see here, for example, some of the explained components. This is the scaling factor. The tension layer has the dot product. The multi-head is set to be true, and also includes a causal mask. And on here we can see the dropout layer. This represents the residual connection, as we can see in the net graph of it. This would be like this connection going all the way directly to the next layer. And this is the tension mechanism that is for the dropout layer, and here there is the normalization layer. All right, so the next component, the next layer that these models use is the so-called feed-forward layer. So the feed-forward layer is a fully connected neural network that consists of two linear layers with an activation function in between. In our case, we're going to use this Gaussian error linear unit, element-wise layer. You can check in the documentation. There are like several other different activation functions that are nowadays used in deep learning. So the first linear layer maps the input into a higher dimension space, while the second maps the output back into the original dimensionality. So the purpose of the feed-forward layer is to introduce non-linearity and allow the model to learn more complex features from the output of the self-attention mechanism. This non-linearity is achieved through the activation function, which applies a thresholding function to the output of the first linear layer. And we can construct it in this manner here. And we can see here there is also a residual connection plus a dropout normalization layer. And in between the two linear layers, there is the activation function. In our case, is this Gaussian error linear unit. So finally, we have all the components that we need for building up the whole decoder-only transformer that GPT models use. And here I added some other hyperparameters, how many of these attention blocks we want during the experiment I was doing. I tried it with 2, and it seems that with 4 different blocks, it also improved a bit the model. So we add together the different components that we saw, the embedding of the tokens and the positional embedding, and then there is a stack of 4 different attention blocks. And finally, there is the output that we add a linear layer and a softmax layer at the end to generate the distribution of predicted tokens. So now we only need to create the training model, and that's by adding a cross entropy loss layer as the final layer of the network in order to calculate the loss between the predicted output and the true output using net train. And basically, the cross entropy loss is a standard loss function used in many natural language processing tasks, such as language translation, text summarization. The loss is calculated by comparing the predicted output of the true output using a probability distribution. And we will see that the cross entropy is then back propagated through the network to update the weights of the network in order to minimize the loss. This is done using an optimization algorithm, such as the stochastic gradient descent. We will use a similar one called Adam. And in our case, which iteratively updates the weights of the network to reduce the loss. So the final training net, it's going to be like this. Here we can see that this is the decoder-only transformer, and this is the cross entropy loss layer. So now we are in a position that we can train our network, our GPT model. We need to specify the model that we want to train, and then include all the lines from Shakespeare plays. Here I specified that I only wanted to train it for 3 rounds to train it on my laptop in a reasonable time. Then the validation set was 10% of the whole lines. I think it's around like 10,000 lines for the validation set. And I specified a batch size of 16 here. So in this case, it took me 1 hour and 20 minutes to train these 3 rounds of training with all these lines. And you can see that I could have kept the model training, since it was still like learning. The loss was going down, and as well as the validation loss. So there was no overfitting. So basically, both the orange and the blue line, they should keep converging. But anyway, we can already like try out the resulting net. I also save it into the Wolfram cloud, so you can directly try the trained net without the need to recompute. Of course, if you had a GPU in your laptop, you can try to train it in GPU. It's going to be much faster. I use the CPU on my own personal laptop. So this is the final trained net. Now what we need to do is to create a predictor. So that's basically, we're going to generate full sentences by iteratively getting the next token prediction from our model. At each iteration, we will append the predicted novel back into the input, and we will repeat this process in a autoregressive manner. So here, as I want to mention that this is not the most efficient way of creating the predictor, since we are kind of computing over and over certain parts of the network during the generation of the sequence. We could, if speed is an important thing for our application, you could use the net unfold built-in function in order to make it more efficient during the decoding process and avoid computing over and over certain representations. So here we can use since it's fast enough for kind of toy examples, we can use nest while list and tell the predictor to stop whenever I take out the end of sentence token, or whether the sentence is longer than 20 tokens. So and I am initializing the sequence with this token, the O token. So it generates, oh my lord, comma, I am a man, a man is a man. So it looks like a bit repetitive. That's mainly because our model it's a small GPT model, and it's parroting, but also we can improve these results by not just picking the highest probability or token each time. This is called the greedy sampling or the greedy search. But we can use some other most advanced sampling methods. So we can introduce some stochasticity or randomness during our generations by sampling from the probability distribution instead of being greedy. This will allow us to generate different sentences giving the same input, and also we can obtain better results, a bit more creative. Here there's a link on a good tutorial explaining the different sampling methods. That the most common ones are top K, top probabilities, and also the temperature hyperparameter. If we increase it, it will generate a bit more creative sentence in a manner. So one can specify the sampling method directly on our model by indicating that we want, for example, to set up a temperature of 0.7. We will get such sequences, "Oh my dear sweet fellow!" exclamation mark. Or alternatively, we can also pick up the top 3 probabilities and start with from the same token. We get, "Oh, what is the matter of my heart?" question mark. And so now we can generate a batch of such sentences. But first, here I'm randomly picking up certain words that start with uppercase in Shakespeare plays. Also, keep in mind that if you introduce here a token that is not in Shakespeare plays, the model will the token will not be part of the vocabulary, and it will not be able to run. So this is a sample of 30 such lines. Most of them are still like nonsensical, but they look more. Some of them look like more in the style of Shakespeare, and there are like even some of them are like a bit funny. So I will stop here improving my model, but here there are like certain improvements that we could do in order to make it more coherent, to obtain a more coherent Shakespeare play. Yes, there is a question from Bob saying that is there a better tokenizer? Yes, that this byte pair encoding tokenizer that will generate sub-word tokens will make a better kind of more suitable for having a more robust tokenizer, and that's the, and I think in the Wolfram language we have included sub-word tokenization as well. For the purpose of explaining of this tutorial, I thought it was more easily, or also for training, it was I think it was a bit faster using one-word tokens instead. But yeah, definitely using a sub-word tokenization would be the next step to make a better tokenizer. I think so. One things that we can do is to scale up the model. So we increase the number, the dimension of the embeddings, as we saw that we use it as small embedding depth dimension. It was 128, but in large GPT models, they use several thousands. We could also increase the number of the decoder blocks, increase the number of heads in the causal multi-head self-attention, increase the length of the training sequences. Putting together multiple lines of the model might be able to generate multiple lines that are coherent. But keep in mind that increasing all these parameters will also increase the training time of the model. So we should probably get access to some external GPUs. And finally, as a matter of a comparison, I created an equivalent Shakespearean GPT directly using OpenAI GPT models. So here, what I did is to use the OpenAI link, which was created recently by Christopher Wolfram. So one needs to install this packlet, and then also create a user account on the OpenAI side and generate your own API key. And then we only need to create kind of a prompt that will do that. By default, the auto completion of this OpenAI link is going to use one of the most advanced GPT-3 models called Da Vinci model. And here, this is going to be our prompt. I'm asking GPT-3 to write a fragment of a play that imitates Shakespeare's style. The characters are Romeo and Juliet, and they talk about artificial intelligence and whether machines will be able to love one day. Here, there's a fragment of a play from Shakespeare as a reference. So I'm copy pasting a fragment of one of Shakespeare plays, and in order to make use of the fact that these large language models are few-shot learners. So if you could give a specific task, it's better always to show them an example. And here there are the results. They're not bad, much better than our GPT model from scratch. And this is one that I tried that even give multiple lines. And then at the end, I'm also adding some useful resources that if you are interested in learning more about GPT models or transformers in general, these are good resources to keep learning. And this is the first one is it's a good place to learn machine learning using Wolfram language. This is a book from Etienne's Bernard. And there is a nice chapter on deep learning methods using Wolfram language. The book is available for free online, and you can also get a printed copy. There is this other blog post from Jalamar, the illustrated transformer. It's a good place to also to understand better the transformer models. And then there is a couple of good reviews on the different attention mechanisms used nowadays in transformer models, as well as a good review on different transformers like used nowadays. It's a fast evolving field, so it's hard to keep the pace of all the different architectures that are being built. But if you understand, once you understand one of the transformer architectures, it's fairly easy to understand the other ones. So then I'm explaining how to generate the header images at the end. Here I used also the OpenAI link, that packlet that we saw before. And in this case, I'm using the OpenAI create image instead of the auto-completion one. And here I got some inspiration for the prompt using this Prompt Hero Hub website, and it will give you some tricks to get what you want. In this case, I wanted a portrait of Shakespeare next to a robot that was a bit sad. And I got several different outputs. Yeah. And finally, since yesterday, OpenAI kind of announced the GPT-4 model on my ChatGPT Plus account. I got early access on the GPT-4. So I wondered, let's try and compare with the same prompt as before to generate some output. And to be honest, it generated a much longer output and also quite in line with her Shakespeare style, talking about kind of artificial intelligence and whether machines will be able to love one day. Yeah, so if you have questions, you can reply onto the community post. In the future, I will share more kind of related topics on transformers on the community. And so thank you for joining me today, and stay tuned for following discussions on transformers. Thank you.